Okay, let's jump into a talk by Mohsen Lessani on compositional verification of distributed systems.
Good morning. I'm going to talk about TLC, Temporal Logic of Distributed Components. I am Mohsen Lessani, an assistant professor at the University of California, Riverside. My student Jeremiah Griffin, that is actively working on the Coq framework, is present in the conference. The other students that help me are Narges Shadab and Shije Yin. Distributed systems are critical to reliable and scalable computing. However, they are complicated and prone to bugs. To manage this complexity, network middleware has been traditionally built in layered stacks of components. The state-of-the-art for verification of distributed systems does not consider either compositional reasoning, program logics, or liveness properties. We present TLC, a novel program logic for compositional verification of both safety and liveness properties of distributed system stacks. This project includes a layered and functional programming model to capture distributed components, a temporal assertion language to specify both safety and liveness properties, compositional verification of distributed stacks, a novel program logic that supports intuitive reasoning steps, and an operational semantics for distributed stacks and the soundness of the logic. We successfully applied it to compose and verify stacks of fundamental distributed components. The ultimate goal is to build certified distributed middleware, and towards this goal, we are mechanizing our proofs in Coq. We present a layered programming model to capture functional implementations of distributed components. A component receives incoming requests from the parent component and incoming indications from the subcomponents. It defines two handler functions, request and indication, for these events. It also defines a handler that is periodically called. These handlers return a triple, the new internal state of the component and the list of issued outgoing requests to subcomponents and outgoing indications to the parent component. Let us consider the perfect link component that uses a stubborn link subcomponent. We abbreviate their names as PL and SL. SL repeatedly resends messages so that they are eventually delivered. This results in multiple deliveries. Therefore, PL is built on the top of SL to eliminate duplicate messages. The state of each node stores counter, the number of messages sent by the current node, and also received, the set of received message identifiers. Each message is uniquely identified by the pair of the sender node identifier and the number of the messages in that node. Upon a request to send a message, the counter is incremented and the message is sent together with the new counter value using the SL subcomponent. Upon a delivery indication of a message from the SL subcomponent, if the message is already received, it is ignored. Otherwise, the message identifier is added to the received set and a PL delivery indication event is issued. Here we briefly illustrate the propagation of events across the stack. We have a stack of components on the left and a trace of events on the right with events at different levels. A request at the top level results in a request for the left subcomponent that in turn results in a request for its own subcomponent that results in an indication, and another indication up, and finally an indication at the top level. In the next slides, we will use the indication identifier D of an event, that is the reverse list of branch indices from the top component to that event. We now take a look at parts of the assertion language. We use the classical operators always and always in the past, and eventually in the past. The assertion A strong implies A prime is syntactic sugar for always A implies A prime. The assertion A leads to A prime is syntactic sugar for always A implies eventually A prime. Similarly, the assertion A preceded by A prime is syntactic sugar for always A implies eventually in the past A prime. The flexible variables for the elements of an event are the identifier n of the node that executes the event, the location identifier d in the stack that the event is executed at, the output requests ORS, and output indications OIS that the event issues, and the pre-state S and the post-state S prime of the event. We use the syntactic sugar assertion self to describe events that are applied to the top component. Now, two important syntactic sugar. Here, down arrow denotes a request and up arrow denotes an indication. This syntactic sugar describes an event at node n at the top level location t where the request event send n prime and m is executed. The bullet is just a separator. And this second syntactic sugar describes an event at node n at the child location 1 where the indication event deliver n prime and m is executed. The specification of both safety and liveness properties of the perfect link can be written almost verbatim from their natural language descriptions. Let's see reliable delivery as a liveness property. If a correct node n sends a message m to a correct node n prime, then n prime will eventually deliver m. A no-forge property as a safety property. If a node n delivers a message m with sender n prime, then n prime has previously sent m to n. And a similar no-forge property is stated for stubborn links. Let us consider compositional verification. We have two stacks S0 and S1 with the specifications I0 and I1. To implement a new component C, we use them as subcomponents. We want to verify the specification A for C based on only the specifications and not the implementations of the subcomponents. A fundamental question is how the specification of a component should be lowered to be used as a subcomponent. Lowering is not possible for every assertion. We observe that lowering specifications requires certain information such as the location of events to be present and certain operators such as next to be absent from the specification. We identify the subset of the assertion language that is both restrictive enough to allow the definition of the lowering transformation and expressive enough to represent specifications. The lower function first pushes and then restricts the assertion. We visit each one of these two functions in turn. When a component is used as a subcomponent, its events appear at a deeper level. For example, the location of the events of the first component are at the top level shown by the empty path. But when the component is used as the first subcomponent, the events appear at branch 0, written as the path 0. The push transformation pushes the locations under branch I. The important case is the atom case. The location D is explicit in the atom. Appending I to the location D effectively pushes the events to branch I. Next, the restrict function. When a stack is at the top, all events belong to that stack. However, when it is pushed to a substack, it's not alone anymore. Its events are interleaved with the events from the sibling substacks and the top component. The restrict transformation restricts the specification to remain valid on traces that are extended with interleaving events. The important case is always A. After pushing, the assertion always A does not necessarily remain valid. It remains valid on only the events under that branch. Therefore, the restricting condition of being under branch I is added. Let us take a look at a few basic and derived inference rules of the TLC program logic. The basic inference rules capture the fundamental reasoning steps and fit in half a page. Yet they provide the basis for the derived rules and verification of full stacks. Here we consider two basic rules and one derived rule. The judgments of this form states that under the assumed assertions gamma, the assertion A holds for the component C. The rule OI for output indication states that if at a node N an output indication E is issued by a self-event, then eventually at N and the top level T, the indication event E is executed. The rule OI prime states this relation in the opposite direction. If at a node N and the top level T, an output indication event E is executed, then in the past at that node N, the indication event E should have been issued by a self-event. Let us now look at the derived rule inv-L. This rule reduces a global temporal invariant for the component to non-temporal and local proof obligations for its handler functions. It states that if a non-temporal assertion A holds for all the three handler functions of the component, request, indication, and periodic, then the assertion holds in every self-event. Thus, the functional implementation of the component can be used to derive invariants. We showcase TLC with the example proof of the no-forge property for PL. If a PL delivery event is executed, it is preceded by its corresponding PL send event. Starting from the PL delivery event, the first step states that if a PL delivery event is executed, the event should have been previously issued. Then the step 2 shows that if a PL delivery event is issued, it is issued by an SL deliver event. And step 3 uses the lowered specification of the no-forge property of the SL subcomponent. Every SL deliver event is preceded by an SL send event. And the other steps are similar. By transitivity of precedence, we get the no-forge property for PL. These steps can be captured in TLC. Here we look at step 2. We want to prove that if a PL deliver event is issued, the issuing event is an SL deliver event. To prove it, we use the rule inv-L that we saw before, with this assertion as A that states that a PL deliver event is issued by only an SL deliver event, and the definition of the component as C. The first obligation is for the request handler. The request function issues an empty set of output indications, and so the assertion A trivially holds. The next obligation is for the indication handler. It issues a PL deliver event, but that is when an SL deliver event is processed, so the assertion A holds. And finally, the obligation for the periodic handler trivially holds in this component. This results in this assertion that with a simple rearrangement is equivalent to the assertion in step 2. We define the operational semantics of distributed stacks. It models the propagation of events across the stack, message passing across nodes in partially synchronous networks, and crash stop failures. We proved the soundness of TLC. TLC derives only valid assumptions from valid assumptions. We also proved the soundness of lowering. If an invariant is valid for a stack Si, and Si is a substack of a stack S, then the lowered invariant is valid for S as well. We successfully applied this approach to a stack of fundamental distributed components, including stubborn links, perfect links, best effort broadcast, uniform reliable broadcast, and epoch Paxos consensus. And towards the goal of certified middleware, we are mechanizing our proofs in a COG framework. I invite you to read the paper, and I will be glad to answer your questions.
Thanks, Mohsen. In either time band, you should now see a link appear in Clowder to join the video Q&A with Mohsen.